Hi everybody, and welcome to this webinar. My name is Kathleen and I'm a geologist working for data mine software in Johannesburg, South Africa. We've got a pretty big turnout for this webinar, and so let's get started. The purpose of this is to introduce advanced geostatistics, which is a new module inside Studio RM. It stems from a collaboration between Geovariances and data mine, where we are implementing Geovariances high-end geostatistical algorithms into Studio RM. During this webinar, I'm going to be running a couple polls, so feel free to join in and just click the results. At the end of the webinar, I will go through these polls and we'll also have a bit of question time. So Geovariances are a research and commercial organization based in France, and their algorithms are rather high-end. So what we've aimed to do with this is to leverage those tried and trusted routines into our very strong geological and block modeling environment of Studio RM. It also makes some of these high-end algorithms more accessible to your average user, rather than just sitting there with the experts. After this introduction that I'm giving now, I'll run a live software demo in beta software and show you what the module looks like and some of the key features inside it. So the part of the workflow that this module fits into is your grade estimation and choosing the parameters that you're going to be using for your grade estimation. So imagine at this point you have a database of samples and you've understood the geology, you've modeled the geology, created some surfaces and solid wireframes, you've got an understanding of your domains, your contact relationships, and really what you would expect to see in that model. And this part is now where you would estimate those samples into your model to try and get a realistic representation of what you're seeing. DataMine released the first version of ordinary kriging in our software back in 1983. I'm sure some of you weren't even alive yet, and the rest of us were all pretty young back then. It was during this phase that the mining industry was coming to grips with kriging and working through it, and during that phase they started to accept it as a standard method of working, which was probably around about the mid-90s. Since then, DataMine have introduced a whole whack of other methods into our software, some linear, some non-linear, but it's now not the time to cover all of those. So the one that we're launching in this module is multivariate kriging, or co-kriging really. So this is where you do a linear estimate of two variables together, and you make use of the covariance relationship between the variables to achieve a better estimate of both. What you aim to do is to often fill in the blanks of a secondary data set where you might not have a lot of sampling data. So this would then use the trends you see in the primary data set and model those into the second, so that whatever correlations between those data you find in your samples, you will see similar correlations in your final model that you produce. I feel the reason that co-kriging has always been a bit difficult in the past is because modeling of cost variograms is rather tricky. There's quite a few rules and constraints that you need to stick to, and modeling of cost variograms it's not quite as easy to understand as modeling of ordinary variograms. The actual execution of the function is quite similar. However, the software takes care of that complexity. There's a lot of tricky matrix math stuff that happens in the background, but really that's largely been taken care of. But that's not to say that you shouldn't try and get an understanding of what is happening in the background and how the weights are assigned to your samples. Okay, so let me get on to the workflow. So these are the large activities that this workflow covers. Scenario management and selecting of samples, these are slightly uninteresting. This is just enabling you to save all your settings so you can always come and revisit a project later, and choosing your samples and your domains and having a look at some bivariate statistics that the system creates. Then we get onto variography, and this is where the fun stuff happens. So the first step we have in there is looking at an anisotropy model. So this allows you to look at a variance model in 3D and rotate that variance model so that you can identify the presence of and the orientation of any anisotropy that may be found in your data. Then you can read that orientation and use that to generate some experimental variograms in the directions of in the direction where you find the most variance and the direction where you find the least and the perpendicular angles to that. Then we get on to the automatic variogram fitting and also manual variogram fitting. So this is a really flexible module, and we hope that it encompasses everything that users need here. You can select a whole assemblage of data, work with several elements, and create a model that fits all of those. And yeah, it's pretty cool. The next step is K&A. So K&A stands for Kriging Neighborhood Analysis. Sometimes it's referred to as QK&A, Quantitative Kriging Neighborhood Analysis. And this is a particular technique where you are able to run a series of tests on your data so that you can make a choice about the optimal parameters that you want to use for kriging. The next section is the multivariate estimation, and this is a sort of a wizard that guides you through setting up all the parameter files that are then going to be used in your estimation. Okay, so let's actually have a look at the software, because I'm pretty sure that's why you guys are here. Okay, I'm going to be doing this demo on the Isaacs dataset, which is a two-dimensional dataset which has two variables inside it. It contains the variables U and V. So U has been sampled everywhere, and you see here the points file. It's two-dimensional. And you can see that there's some high-grade areas where there's slightly more dense sampling and some lower-grade areas as well. We have a second set of data, or not a second set, sorry, a second variable of data, which is U. So let me do a legend for that. And you'll see quite clearly there that U has not been, oh, sorry, I think I lost the audio connection there for a second. Let me just repeat that. So we have two variables in this data set, V and U, and V has been sampled everywhere, whereas U has only been sampled in certain areas, and it's sort of clustered in the higher grade areas. I've done a couple scatter plots of this data and some histograms. So the histogram for U, which is our secondary data, is on the left. And you see it's got a slightly skew distribution with a bit of a tail. And then V as a sort of a slightly more normal distribution with the median and the mean sitting closer together. And V's also got more sample data, 470 versus the 273 sample points of U. And some of the samples in the low-grade area are not reflected in the U. So V's got maybe data spread over two domains. If we look at a scatter plot of this data with U on the x-axis and V on the y, you see there's a positive correlation between those of 0.54. But as the values of U increase, so the values of V increase. So now let's get on to estimating these. While I load that up, there's just another poll quick. So we run this as a button, as a multivariate estimate button. And we're first going to select our scenario. So I'm going to work with a scenario that I've set up beforehand, just as we have limited time here and I don't want to spend time waiting for things to run. So here we select our sample data, and I've selected the fields U and V. So the system automatically creates a couple statistics about those. It's measured the distance between all of those samples. So we can see here that the average sample distance is 133 meters. Going back to the samples. And the closest samples are 2 meters apart. It also produces some bivariate statistics, so we can quickly see how many samples are co-located. So co-located is when when a sample has two elements analyzed in exactly the same spatial location. So V has 470 samples, but those are not co-located with U. There are also some other statistics like the correlation between those and also the covariance, and there's some others. With the covariance, it also just shows the variance of V and the variance of U plotted in this matrix. Now we're going to take a look at the variography. So this is where we create a 3D variance model. So now we're creating one. I've chosen to create it on U because U is my element that has a better spatial representation than V. So you see there are 4 windows produced. Now, the 4 windows would be used in a situation where you have a 3D data set, and it would allow you to orientate your data in the Y and X plane as well. But now I'm only going to be rotating around the Z axis because it's a 2D data set. So what I'll do here, I'm just going to zoom in a little bit. And you're looking at, in the top left window, we're looking at variance contours. So what I'm going to do, I'm going to align the orientation of maximum variance with my north axis. In the top left window, top right window, you see these intersecting planes, and that's showing the orientation of each of these individual planes. Now, when I create those variograms, I can come and read that orientation from that window and use that so that I create my variograms such that they're aligned with these orientations, these directions of the most anisotropy. So this is the window that you see when you create your experimental variograms. You select the grade fields that you're interested in, and you've got a couple options of which variograms get created. So you can create your downhill variogram, which would give you a good idea of what your nugget would be. But since these are points, we don't have any downhill variograms. These would also ignore any orientation you have and work with the samples and the boreholes to create that variance, and not the orientation directly down in Z. We also can choose to create cross variograms. If I unselect this, it would just create a univariate variogram, experimental variogram of U and of V. And we can also calculate directional variograms. Ticking this box gives me access to these lower 2 windows on the right. The top one is the horizontal directions. So here you can set about adjusting a fan so that you can create individual variograms in those orientations. For this demonstration, I'm just going to create 4. And you also then have your vertical directions, which is I see I've lost the audio connection again. I'm not sure if you're able to hear me, but I'm going to carry on. So the vertical directions would then show the perpendicular orientation to your XY plane. Next, creates a smoother variogram, which is easier nicer to fit your model to. we can also come and display the number of sample pairs, which is pretty useful. So you can see which points you have a bit more confidence in because they have more sample pairs. So let's have a look at the two perpendicular orientations, which is 0, 0, which is sort of pseudo-north, and 90 and 0, which is the XY. So these obviously align to this north orientation here, which is a rotated north and an east-west orientation. To choose the variograms that you would like to view, you work with this matrix on the left, where if you click in the UU window, you'll see the U variogram, univariate variogram, and the V univariate variogram. And in the cross variogram, you select by clicking in the cross box. You could also view both variograms together. So with the auto-fitting, what you do is you basically just click Run Auto-Fitting. And the system will then go and generate a variogram using the best fit onto that set of data. Let me jump back to an earlier one. We can also come and modify these points. All of these points are dynamically modifiable, so you can come adjust your nugget, adjust your sill, and it always constrains your fit to positive definite. So sometimes you try and move a point and it's because it's constrained. You can come and remove those constraints as well. With the auto-fitting, you've also got a few things that can guide the system. If perhaps you want to have a second structure sitting between 50 and 100 meters, and you can provide that constraint, and then the system will look at those rules when it does the auto-fitting. There's also a full set of tools to do manual fitting if you don't want to use the auto-fitting tools. And you can also come here and review all your variogram parameters or type in values. Okay, let's get on to the next part of this module, which is the KNA. So the KNA allows you to test representative areas for your kriging parameters, and the first thing that we're going to do is select those areas. So what we'll do is we'll pick a well-informed area, which would be somewhere where there's a lot of sample data, and we then click here to get that point. Now, I would do the same then for the moderately informed and an area with sparse sampling. Now, occasionally you can get a fair bit of bias in your KNA results because of the block you chose. So to mitigate that, what we've done is we've run the KNA tests on a grid of blocks, and you can specify what that grid is by choosing how many cells you would like to test on in each direction. So in this case here, we're testing on 3 in X, 3 in Y, and 1 in Z. Sorry, I think the audio is sometimes a little bit, it breaks now and then. Okay. Anyway, so we're testing these 3 points, the well, moderately, and sparsely informed. What we next do is we select a block model as a base. You don't have to pick a block model, but if you do, it will use the block size from that model in your it will guide it through the KNA testing and help it set up some default parameters based on that. So now we're going to get into the optimize. So I'm going to look at some tests that I ran a little bit ahead of time. The 3 main areas are optimize your discretization points, your block size, and then your search neighborhood parameters. And the idea is that it's not a workflow where you're forced to go from the first to the second to the third test. It's that you can run all these tests interactively and jump backwards and forwards and run the tests that you want to run in your data. We're not at all being prescriptive about the parameters you need, but we're creating a platform of tools that will allow you to experiment with your own data and find the parameters that are suitable for you. There is no pure recipe for how KNA should work, so it's meant to be an interactive tool. So looking at our discretization, here we look at the how the block covariance varies when we add more discretization points. So on the chart, we're looking at block covariance on the y-axis and discretization on the x-axis. And we see that as we increase the number of discretization points, they're viewed now as a line chart, but we can also view them as a scatter. And we see that this number decreases. Now, I'm sure you would have all noticed the spike in values here. And this is because we ran two tests together. So we've tested the x values from 1 to 15 in increments of 1 and the y values at the same time. But I chose to do a test on reduced combinations. So this meant that for all the tests in x, it always used the parameter of 6 discretization points in y, and obviously the converse applied for the other tests. To make those results look a bit easier to interpret, that's why we look at it as a line chart. You can also view this with the min and max. Now, what the min and max here are showing is the variance in the grid of points that you ran, because we selected a single location, but we did the test on a whole lot of points as well. So the mean value shows the average of those, but obviously there is some variance based on exactly where you are. Looking at the optimized block spacing, I'm just going to load some previous test results. So here I did a test on a single value at once. So I looked at my block size in X testing from a minimum value up to a maximum value in a particular increment. And then what we get is a whole lot of measured values, which we can look at. So here we're actually looking at the estimated grade, but we can have a look at the kriging efficiency. And here we see that as we increase the block size, so the kriging efficiency increases. And your kriging efficiency is kind of a measure of your smoothing. And what you would do is you would look at a whole lot of different measured values in parallel to get an idea of where they converge and where the other one changes to make an informed choice of the parameters. The charts also split into the different areas we're looking at. So here we have well-informed, but we also have for the moderately informed area and as well the sparsely informed. Lastly, we'll have a look at the values for the search neighborhood. So here you can run a series of searches based on the size of your search ellipse, and then also the number of samples you're using in your sectors. For the DataMine users who are familiar with Estima, you'll notice that some of the terminology we're using here is slightly different than what we were using previously. For example, here we refer to optimal samples as they are used in Geovariances, our status software. And the optimal is slightly different to the maximum because your optimal is equal to your maximum times by the number of sectors that you're estimating. Okay, so here what we're plotting is the optimal samples per sector, and we can actually have a look at the number of samples, and you see that through this test my number of samples is increasing, and that obviously has an effect on my values, like my slope of regression is increasing quite dramatically up to a point. So here we might say very rudimentarily that 15 samples would be a good thing to aim for here. So we really hope that this platform is going to be something that can be used and tested and really pushed to its maximum to help you guys make better estimates. Okay, now let's quickly get on to the actual estimate. So what we do here is we're going to select an underlying block model, which I created in advance, just a 20 by 20 meter block model that covers my sample area. Then we come and we define the estimate. So we're running a multivariate estimate, a multivariate ordinary Krig with X and Y. I set up my cell discretization, which is based on my KNA analysis, and I choose what type of output I would like to have. So we can have a fairly simple output of just your estimate and your Krig variance, or you can have a look at all your parameters. So we also have a list of the field names that get created. and you can come and modify these as well if you wish. We have a look, just to have a look at what gets graded. We have our estimated value, which takes the default name of our grade field underscore E for the estimates, with some other ones like the weight of the mean, the sum of the positive weights. It's also a little bit different to the old way it was done in data mining, the sum of negative weights, and your slope of regression. Next, we come and select the variogram that we'll be using for this estimate. And you can also review that variogram and have a look at the structures inside it. Then we come and set up our search. So you have several windows here where you can come and choose what your ellipsoid size is. You can visualize that ellipsoid and set your number of samples as well. We have a button here to create your search volume based on your variogram. Now, I know that's not always it's not always the best way to do it, but it creates a starting point. And the reason I say it's not the best way to do it is that if you have a very continuous data set, you might find that your variogram range is a lot smaller, your search ellipse is a lot smaller than your variogram range. And if you have a very nuggety deposit, you might find that your search is much bigger than your variogram range. Anyway, I digress. Now we get on to running the estimates, and this is really just a summary of the different parameters that we've used. So it tells you what output you've selected, what variables you're estimating. You're also not limited to running one estimate here. We could be running in parallel a couple of univariate estimates or different multivariate estimates using different parameters at the same time. So we're going to run that estimate. It's been successful. I haven't shown you, but in the command window, there's a whole continuous sort of dialogue of what I'm doing as the things run. So let's have a look at that model. So my block model's been loaded. Let me set a grade field. We'll first look at the V grade field. There we go. And I'll set my sample data to the V grade field as well. So what we see is there's a high grade area here, and then the deposit moves onto a low grade area here to match your samples. And if we were to look at some of the other indicators like the slope of regression, we'd see higher slopes of regression in these areas and lower slopes of regression here. But what I want to draw your attention to is this bridge between the area here, where my mouse is, and this area here. And I'm going to change the block model now to my secondary variable. And the points as well. So remember how the secondary variable had very little data in this area. So what essentially would happen if we were to run a univariate estimate would be that this high-grade area here and these high-grade samples here would probably smear high-grade across this area. But now when we look at the model that's been estimated using co-estimation, we actually see that this grade area here shows a couple, like some low-grade blocks. And this is because it's followed the trend of our high-grade area. And that's one of the benefits of a multivariate estimate. Okay, that's the gist of the module. Now we're going to just have a look at some of those poll results from some of the tests that the polls that we ran. I have a last one. And then if you'd like to ask any questions, we don't have a lot of time, or I guess we do, we have 5 minutes. If you would like to, if I'm unable to answer any of your questions, I'll get back to you afterwards. And if you would like to sort of continue the discussion, you can do so on our LinkedIn forum, or you can contact someone at your local data mine office, or even contact me directly. I'd be happy to chat to you further. I'd be interested to hear what you think of the module, if there's anything you think is missing or would like to see in a future version. Yeah. Okay. So are there any questions on the K&A? Okay, I don't understand the question fully. It's I can only see half a sentence. Oh, wow. Okay, sorry, the quick poll was covering the screen. I'm sorry about that. I hope you still got to see enough of the webinar. Okay, I see as well, some of you lost audio during that. I'm very sorry about that. Yeah, we're down at the tip of Africa. Our internet isn't always perfect here. Okay, there's a question from Anton. He asks, do the parameter files have the same structure as for estima, between est, search parameter, and vmod? We've tried as far as possible to keep these parameter files the same. However, there are some additional fields that we've had to add, and we're working on making sure that these parameter files are compatible. The reason for this is the variograms are now cross variograms, and those contain a couple additional fields. So a variogram is no longer a single line. So we had to introduce some extra reference fields so that those different lines in the file are linked together. So yeah, they will be compatible. Okay, the next question I don't understand. Okay, can I show you how to validate the model? There are a number of ways of validating the model. We could use swath plots and some other things. I don't have time right now to show this, but I'll contact you directly, and I will also, we could maybe show this in a future webinar. Okay, how can we find the optimal search ellipse? That's a good question. So what's often found as more important than the search ellipse is actually the number of samples, because the number of samples will often be smaller than your search ellipse. So I think what you often need to concentrate on is the number of minimum and maximum samples that you use for your estimate, and just ensuring that your ellipse is big enough to allow those to be found. The ellipse is almost like an extended constraint. And the size of your ellipse should really relate to your anisotropy being longer in the one direction and sort of smaller in another. Okay, how does the licensing work for this module? So there's an additional license for this module. It's an add-on. The module will be called Advanced Estimation, and we'll have to speak to you all individually about that. Okay, I'm using a beta version of Studio RM. This is not yet available for public release. We're still in the final testing phases and sort of getting out the last things. We're not going to release anything that is, not yet perfect. Okay, there's a question about having normalized and unnormalized variograms. We will have the option to have normalized variograms. Sorry, in this example, I was just showing the unnormalized variogram. Oh, the questions are coming thick and fast. Okay, can the estimation process be recorded into a macro? The background, there is a macro that you can run, so it will be available as a co-kriging macro, and you can actually use that in your own scripts and macros. I'm not certain about the recording, but you will be able to set up the parameter files using the wizard, and then refer to those parameter files if you're writing your own script or macro, and introduce those when you're running it. Okay, there's a question about doing drill space analysis. That's not something which we've built into this module. There are other ways of doing it, Derek, and I'll get hold of you after the session. Okay, will the variogram construction replace the varfit? So varfit is the really old way of doing the estimate. And it won't replace it. That's going to sit there as a legacy module in the background, but I really hope you've all kind of moved on from there. Okay, there's a question about the line showing the total variance. Yeah, we have that in as something which we are going to put in, so you will be able to see the variance as a line. Okay, our time is up. For those of you who want to go, you can go now, but I'm just going to quickly run through some of those poll results if you're interested. There we go. So how long have you been using Datamine? Oh, it's great to see that there's some old users here. 37% of people have been using it for more than 10 years. Okay, do you think KNA is a useful tool? Okay, so I see a lot of you are already using KNA. And have you ever run a multivariate estimate before? No, yes, I've tried it a few times and only a few of you are experts. Okay, thanks very much. And as I said, if you'd like to get in touch, please feel free to email me or maybe perhaps start a discussion on this on the LinkedIn user forum. Cheers.